the job of paint is to send light back at you. It doesn't create light. It sends light back at you from the room, and it tries to work with that light in some strategic way to make you see what the person who painted it wants you to see. So first off, it has to work with the light in the room, and that can vary depending on what sort of lighting you've got. And you already have seen that if you use sunlight to light the room, as opposed to, or alternatively you use incandescent lights, the old-fashioned Edison light bulbs, that illumination's different. And hopefully you now recognize that incandescent light bulbs don't make very much blue light. So it's white, supposedly, but it's pretty pitiful in the blue. Not a lot of blue light. So if you're expecting your paint to deliver a nice blue look, and you illuminate it with incandescent lighting, it may not give you what you want. It'll look different in sunlight than it will look in incandescent lighting. And that's a general theme of things, that paints look different in different illuminations. So you have to sort of anticipate what's the lighting going to be like. This is true not only of paints, but of things like makeup. This is a reason why makeup mirrors often have settings to illuminate you with different kind of light, because the makeup will look different in incandescent lighting than it will in sunlight, because there's not much blue in incandescent light. Same with paints in general. You might go to the store and try to match two paints with each other, and they look right in the store's illumination, but you go home where the illumination is different, they won't look the same. And that's a common problem. The only way to be sure you're going to match the paint when you go and buy a new can of paint is to buy the same brand, in fact, the same batch. It's tricky. If you switch brands, you may get two paints that look right, but only under one sort of illumination. Modern technology in the hardware stores got it so they do a pretty good job of matching things for you, computer, but it's a tricky business. All right? So illumination matters. Okay, about the paint itself. The paint typically has two things in it. One of them is something that sends the light back at you, because you don't want the light to just go into the paint and disappear. It's supposed to come back, at least part of it. So they'll have surfaces in there, lots of little surfaces that reflect light. They can put metal in there, and the metal will reflect light, and some paints do, metallized paints. Most paints, however, don't. They have what's known as pigment. So specifically, what's pigment as opposed to dye? And here I get my opportunity to try to tell you. Pigment is a material, typically it's a transparent material that has been crushed into tiny, tiny, tiny pieces, and every surface in that material, whenever light goes in and out of the surfaces, through the paint has a plastic, typically a plastic overall, but it's got surfaces inside. There's a little reflection, as you guys should know from the problem set, and lots of reflections give you finally this light coming back at you. And if the reflections have no particular direction to go in, you get a whitish result from that pigment. If there's a little bit of orientation to the surfaces, you can get these sort of metallized surfaces, where a lot of cars have it, where it's not shiny like a mirror, it's not dull like white paint, it's got a kind of a sheen to it. Well, that's partially ordered surface, the little reflectors. But okay, seeing as how we've got some young first years here, just to show you this, the idea that you can make these reflective surfaces give you the light coming back at you. So I am going to look down on this camera here. I've got some pieces of glass up here. And you now should be looking down on the pieces of glass. And right now they're just transparent, but you can see them by their reflection. A little bit of the light that's hitting them doesn't go in. It bounces off. And that's because light is changing speed. It's slowing down as it goes into the glass. And as it tries to slow down, part of it reflects, about 4% on that top surface. And there's also a 4% reflection as the light comes out the back, trying to go back into air. And right now they're nice, shiny reflections because the surface is flat on both sides. But I'm going to crush one and try to do this without cutting myself to flinders. Here we go, okay? I'm going to cover the glass up so it doesn't fly around. Oh, that's got to be bad for the glass. All right. So now we got lots of little pieces. So there are lots of little reflections. It still looks mostly transparent. But let me see what all right. Let me pile them up and crush them some more. My goal is to get it to become really a pile of white powder, and to do it without getting too much of it in my fingers. All right, come on, guys. Well, there in the center, you can start to see the white. Is that okay? I can keep going all day and we'll end up with a pile of white powder, but every time I try it, I'm risking my fingers more. So what you're seeing there in that center, we can zoom in. And focus. Yeah, it's still tiny little pieces of transparent glass. They've just gotten smaller and smaller and smaller, and there are piles of them there now, and that's about okay. Now that we've zoomed in, I want to make a better pile of it. Okay. So you can see, if you look carefully, the individual pieces of glass, and we could take them apart and each one would still be clear, still have shiny surface. But the fact that there's a stack of these surfaces piled on top of each other redirects a lot of the light back at you and in random directions, so it appears white. Any questions about that idea? I told you the other day, reiterate, modern white paints, and even paints that aren't white, typically have a lot of titanium dioxide in them. It is the white pigment of the present time. It's not very expensive. It's not totally cheap, but it has a very high index of refraction. So when you put it in almost any other material, for example, in plastics, transparent plastics or water, the change in the speed of light and going in and out of that titanium dioxide is still huge, because it travels so slowly in titanium dioxide, and therefore you get a good reflection off of it. And powdered titanium dioxide particles that are separated from one another by at least a thin layer of plastic, that means reflections off every entry and exit surface. And so some of the technology that goes into making, for example, white paper, the white paper, this has titanium dioxide in it, believe it or not. And what they try to do is make sure that the titanium dioxide particles are not touching each other, because if they're on top of each other, touching, then the light doesn't have to go in and out of the material. It just goes from one piece to the other, and there's no reflection. So getting the particles apart, there is technology in that too. The other thing I wanted to show you, before getting back to the physics of a neon atom, you okay?
What about white clothing and stuff?
What about white clothing? White clothing comes about primarily because you have tiny transparent materials in there. I'm not wearing white clothing, so why am I doing this? The other day I was. It's white because it's got tiny fibers, typically of cellulose. A lot of white clothing is made out of cellulose. It's cotton. Cotton is almost entirely cellulose. What's cellulose? Cellulose is actually a sugar polymer. It's a sugar polymer, that is, it's made of sugar, little sugar molecules tacked together as a vast string. And that then becomes a polymer, poly being many. And it is the most abundant plastic on Earth. Cellulose it's the walls of all the plant cell. They're cell walls, so it's everywhere. Trees are made of cellulose by and large. Plants, the insoluble fiber that you're supposed to be eating sometimes? Cellulose. Okay? We can't digest it. Cows actually can't digest it either, but they have help from bacteria that break it down. So that's why they chew their cud and all that stuff, is to help them digest cellulose. It's transparent. And if you have lots of cellulose molecules separated with air in them, so it's cellulose, piece of cellulose, piece of air, piece of cellulose, piece of air, you get reflections off every surface. And so that's why clothing is white, cotton cloth is white. If you get rid of those transitions from air to water to air to cellulose to air to cellulose and stuff, if you get rid of those transitions, for example, by getting the cotton wet so that the transitions are less intense, the cloth becomes more transparent. Same with paper. You get paper. Paper is mostly cellulose with titanium dioxide thrown in to make it whiter. Okay, but just simple paper. But when you get paper wet, it becomes somewhat transparent. Same idea. And that's because the light doesn't change speed very much anymore when it goes from cellulose to water to cellulose to water. Not much reflection. All right? What if there were no change in speed in going from air, from one part of the material to the next, to the next, to the next, no changes in speed? For example, what if you put that glass powder that I created, it's still up here on the screen, what if you put that in a liquid that had the same index of refraction as that glass, so the light didn't change speed in going in and out of the glass? Well, would you see the glass? No. And I can show you that too. I'm not going to do it with this glass piece here, although I guess I could. It'll just make a mess. What I'll do is I'll show you light going in and out of this glass. This is laboratory glass. It's the same, it's basically Pyrex. It's the same glass used for cooking. So this glass has a certain index of refraction, meaning the speed of light in it is a certain value, and I never remembered the value. And it turns out that that's almost the same index of refraction as salad oil. So when you put Pyrex or its equivalent glass into salad oil, most of the salad oil is vegetable oil basically, the light doesn't change speed in going in and out. And you have a serious trouble seeing the surfaces of that material. And I'll show you that. You okay with the idea? I mean, it's not, I've talked about it before, but Hawks West. So there, you're looking in, no. Hi. Okay. So now you can see, you see the surface, presumably, right? Nope, not yet. There you see the surface. And it's, right now, there's air inside the beaker, so that's a flask, so it won't disappear entirely, but as I immerse this in here, the surface, the front surface is gone. All you're seeing is reflections off the inside surface. So it should look a little weird. And let me now instead put in the same sort of flask. Actually, this one has no writing on it, which I'll deal with in a minute. When I put this one in, it should disappear essentially completely. Is that true? Yeah, it's pretty much gone. You see a little bit of, you see a bubble. There was a bubble, was all that was there. But otherwise, it's pretty much invisible in there. There's no transition. Light goes right through the same speed the whole way. What I want to do is take this one, which has writing in it. It's more fun. Let me sink this guy down. So it's always fun to cover my fingers with salad oil. All right. So now we should see the writing just floating in space. Oops, didn't fill it properly. Get the job done here. There's the writing and nothing else. A little bit of lighting would be good, but the camera's actually having trouble focusing on it because it doesn't see much. So there's the writing, otherwise pretty much invisible. Okay? And I believe that people trying to assess whether jewelry is legit, whether the stones, for example, are the real thing or phony. If you can look up the index of refraction of various jewels, and if you if you take a joule that has an index of refraction of 1.82, and you put it in a liquid that's got an index of refraction of 1.82, the joule will disappear except for its color. Its surfaces will vanish. A diamond, it's got an index of refraction 2.4, I believe. If you put it in a liquid, index of refraction 2.4, diamond's gone. Okay. All right? Thanks, guys. So just to finish up with paints. So paints use a very high index of refraction powder to give you that, send the light back at you. Getting the powder the right size, getting the particles separate from one another so they don't touch to the extent that it's possible, gives you the hiding power that, you know, if and when you guys start buying paint, it's sort of inevitable, they'll be pitching their hiding power and things to you. It does matter to you if you've got, unless you've got infinite time and infinite money, it does matter to you how many coats you have to apply before you stop seeing the old paint when you apply the new paint. And so having a paint that manages to put lots of little tiny particles between you and the old paint, and those particles have to have a very high index of refraction, and they should be the right density, not too dense, not so they don't touch, and not low density so they're wasting space, and just basically hide the old paint. This is what you're buying when you're buying paints that have good hiding power. The other thing you often care about, though, is color. And the color comes about by introducing additional chemicals into the paint that truly absorb certain colors of light. So if you want somebody to see a blue, for example, in the paint, you want it not to absorb blue. You want to put chemicals in that absorb everything else, namely red and green, the reds and the greens, that part of the spectrum. And so getting the paint colors involves selectively removing the other colors with dyes. All right? And this is where, if you want to make the colors match perfectly, you literally want to use the same dye molecules, because dye molecules do absorb certain frequencies better than others and stuff, and if you have two so-called red, two blues, they may not, blue dyes, they may not truly absorb red and green exactly the same way, and therefore you'll get differences in different illuminations. Okay. Any other questions you have about paints? Okay. Hopefully that'll be actually useful. There'll come a time when you'll be staring at these things trying to remember what it was I said. Okay. Discharge lamps. So you are currently illuminated actually by fluorescent lamps which involve a discharge. And to get at the idea of how a discharge even works, what it is, we'll go back to a very simple discharge, and that's involving neon. So the neon of neon signs, which are also discharge lamps. And that goes to the structure of the neon atom. Why does the neon atom emit red light? And the answer to that is because of its quantum structure, the way the electrons live inside the neon atom. I told you last time they are not little balls like planets whizzing around the nucleus. Instead, they are standing waves. The electron itself is a wave. It's a ripple. It's technically, and this is an aside, it's an excitation of another field. We've seen the electric field, which can have values at every point in space and have interesting structure like the structure you have in a wave. We've seen the magnetic field. There's actually an electron field too. And you can have an electron field excited and has interesting values at various points in space. And that is, one electron is one of these ripples. It's one of these structures that lives in space. And all the other particles are like that too. We're built out of lots of little ripples in space, excitations of various fields. Okay, so the neon atom has more than one electron. It's got 10. Why? Because it's got 10 protons on its nucleus, and that 10 fundamental positive charges they attract negative charges until the thing is neutral. That's its favorite situation, and so it attracts 10 electrons. They can't all go into the lowest energy quantum wave, and the waves in atoms are called orbitals because they're because they derive, in a sense, from the orbits of planets. Again, they're not little balls whizzing around, they're waves, but so we call them orbitals anyway, in honor of the orbit-like origins. And the electrons will tend to go pile up in the low energy orbitals if they can, because if they have extra energy, then they have more than their fair share relative to their environment, and there's this tendency of objects given any opportunity to exchange energy until the energy is distributed in a thermal, according to the rules of thermal physics, the statistics of thermal physics. And that means having one atom with gobs of energy in its arrangements, and everybody else like bereft of energy is like, that's unfair, it's statistically unlikely. So you end up with all the electrons in a neon atom tending to pile into the lowest energy orbitals that they can, and they would all go into the same orbital if they could, the lowest, but they can't because of this Pauli exclusion principle I told you about last time, that you can't put indistinguishable Fermi particles in the same wave. So the electrons have to go one at a time into the waves, except that they have an internal degree of freedom, a distinction, which we can call spin up and spin down. You can therefore get 2 electrons into every orbital. And that means that you pile, neon's 10 electrons pile into 5 orbitals. And then it's done. It's electrically neutral, it's got no extra energy, it's all happy, until you smash charges into it. And that is the idea of a discharge. What a discharge does is it creates a plasma. And so here's a little bit of story. A question I'll actually ask it. A plasma is a vapor of charged particles. So what distinguishes it from just a gas is that in a gas, the particles are electrically neutral. And they're unaware of each other until they touch. In a plasma, the particles at least include, you can have neutral particles in a plasma, but who cares about those neutral particles? The charged ones are special now. They notice each other at a distance because of the forces between charges, Coulomb forces. So now you got, it doesn't behave quite like a gas anymore because of this long distance interaction that shows up. You don't have to touch a charged particle to know it's coming. Its electric field precedes it. So the question here is why can't a gas conduct electricity? Why can a plasma do it when a gas can't? So plasma, again, being this vapor of charged particles. So first question is, each gas particle has 0 net charge is a reason why. And that's actually the answer. It's another terrible question to ask live. This is a better question back in the days of clickers, which maybe someday I'll resurrect. The other answers are not right. Plasmas don't have to have a net charge. You can have what's known as a neutral plasma, meaning that if you count up all the positive charges in the bottle and you count up all the negative charges in the bottle, and it still sums to 0. It's just distributed funny. You've got some particles actually carrying their own little personal positive charge, and some not. Some having negative charge. A gas contains only negative charges. That's not true. And gas particles aren't mobile. They definitely are. So this is a terrible question in the era post-clickers. The fact is that plasmas can carry current because they have charged particles. If you put a voltage drop across them or electric field there, the particles will accelerate now. The charged particles will pick up speed or change their velocities, and you can drive them across the entire container. So that's what's going on in a discharge lamp. Simple discharge lamp, you just take the 2 ends of a tubular container, and you put a lot of positive charge on one to make it high positive voltage, and you put a lot of negative charge on the other to make it large negative voltage. There's now a big electric field in the tube, pointing from high voltage to low voltage. The usual rules, if you remember that far back. I barely do. And if there are charged particles in that tube, they'll start moving. And they'll pick up speed, and work will be done on them by the electric field. So they'll not only will they pick up speed, but they're going to start to accumulate kinetic energy. And if they smash into stuff, they will potentially knock other charged particles out of what they hit. Say a neon atom sitting there minding its own business with no net charge on it will get smashed by a moving, I don't know, an electron traveling opposite the field because its electrons are negatively charged. And bam, that impact can easily knock an electron out of the neon atom. So in goes one electron, bang, out come two electrons. The original one that was free and one that used to be part of the neon atom. So now you've got a positively charged neon fragment, what's called a neon ion now. And you have an electron that wasn't there before. And this kind of cascading effect can happen inside of a gas when it's exposed to this big electric field. And we've seen this sort of thing before in the corona discharges and in the just sparks and all that. This is just sort of a more, it's kind of a sustained spark and somewhat controlled spark. And that's what's going on right now. When I turn on the high voltage, and the fact that I can hear it hum as it has driven me crazy for years, means that not only is it's a high voltage, it is a high alternating voltage, which makes very little difference. It just means that all the positive charges are first shoved up, and then they're shoved down, and then shoved up, and it reverses with the power line, the 60 cycle that we talked about way back. But in any case, it's glowing away. It is glowing because, first off, it had some initial charged particles. You can't get the discharge started without having at least one charged particle somewhere in the container. And fortunately, those charged particles, they're actually around naturally. Sometimes, in some cases, you have to like push extra ones in there, but they're around naturally because of cosmic rays. I think I've told you that in the past. So they're just, any bottle of gas, you have a few of them that are charged because it got hit by stuff coming from outer space. So here they are, they were there when I first turned this on. Now, they're self-sustaining. The charged particles pick up so much energy as they begin to move, driven by the electric field, that they smash into each other and knock other charged particles out. So the discharge component of this, is that okay with people, or questions about the discharge itself? That is what a discharge is. It's current flowing, I mean, that is, I'll name it. It's current flowing through a plasma, or if you want to be a little less technical, through a gas, which is secretly a plasma. Okay? And there is that going on above you in the fluorescent lamps. It's here. Where else would it be? You know, a lot of signage. Modern technology and light emitting diodes are replacing the neon signs to some extent, but they're still pretty common. And street illumination and large gymnasium illumination stuff. Mostly discharge lamps, or at least have been historically. Okay, now, the reason it's red, which is the reason to talk about all the orbital structure of neon, is because the neon atom, when it's in its ground state, it's quite happy, of course. It doesn't have any extra energy to give up. It can't give up any energy that it currently has, because that would require taking energy from at least one of its electrons and putting it, therefore, into an orbital with less energy. Well, there are no available orbitals with less energy. They are all occupied by electrons, and the Pauli exclusion principle forbids them from going any lower. But if you have a collision between some projectile, like a charged particle, and a neon atom, one that doesn't actually knock an electron out of the neon atom, it might still knock the neon atom into an orbital, knock the electron into an orbital it doesn't belong in, or wasn't originally in, a higher energy orbital, which I'm just naming the orbital as, it's another quantum standing wave that the neon atom can have, and it's one that has more total energy than the orbital it was in previously. Just as a short note about, like, what does it mean to have more energy and why? Well, if the orbital, which is again a standing wave, puts the electron on average farther from the nucleus, then the electron has more electrostatic potential energy. It's farther from this attractive center. So to get it out there, you have to do work on it. You have to add energy to it. So far it's got more energy. Is that okay? The other thing that it has is potentially it can have more kinetic energy. Well, where does kinetic energy show up? In a standing wave. It doesn't really, the wave is sitting there dancing in place. It's not really doing anything. It's not going anywhere in a conventional classical sense. How can it have more kinetic energy? It turns out that the kinetic energy is associated with spatial variations in the wave. If the wave has a short wavelength, basically. So if you look, it's wrapped around around it, and so it's got a ball-like overall character. But if it makes a lot of change from here to here to here to here, if it's effective crests, and the crests I'm using very loosely, if the crests are like tightly packed, so they're close together, that means it's got there's a lot of, physicists call it curvature to the wave function, which is not very helpful, but it has a lot of kinetic energy. It's hard to make rapid changes in the wave. That takes energy. So the orbitals that have extra energy typically are farther from the nucleus, and that gives them electrostatic potential energy, or they are more curved. They have more closer spaced crests, and that gives them more kinetic energy. Okay? It is what it is. All right, so the neon gas, we're seeing, yeah. What was the second one in the lamp, the plasma in a solar storm? What's the difference between the plasma in a solar storm versus neon? They're the same concept. So in the neon lamp, the plasma is pretty much sitting still. It's pretty much a neutral plasma, and how do I know that? Because if it had a net charge, it would tend to expand. Because if it's all positive charge, wow, we hate being near each other. If it's all negative, we hate being near each other. So these things sort of self-stabilize in a bottle to being neutral. So they don't just go off to the walls and hit. In a solar storm, because the plasma is so diffuse and dilute, it's so spraying out charge, it could have a net charge. So you could have a blast of positively charged thingies come flying off. But the fact that they are, so the solar storm, the Earth is bombarded all the time by stuff coming off the sun. A lot of it is electrically charged. There's lots of energy there. It's easy for the sun to take the electrons off of a neon atom, for example, or any of the other atoms that come flying off. Probably most of them, yeah. And so the atomic fragments are probably mostly positively charged. Occasionally you may get a negatively charged atomic fragment. That means it has an extra electron. Getting that electron to leave is typically pretty easy. So I imagine most of the particles coming off the sun by accident are positively charged atomic fragments and free electrons coming at us. Their net charge doesn't matter all that much, whether there's a net positive in a box or a net negative, because it's so diffuse. Here it matters. If you get a net positive or net negative, it's awkward. Things tend to expand as a result. Okay? Okay, if I change the gas, just because I can, if I change the gas from neon to helium, helium's it's a simpler atom. It's only got 2 electrons, and we can make a discharge in that, and there it is. It's different color because the orbital structure is different, and so where do I want to go next? I want to drag this camera over there. The different orbital structure means that when you knock an electron into a higher orbital, an excited orbital, extra energy, it works its way back down to its original orbital step by step. Well, the steps are different in mercury than they are in helium, in neon, because of the structure, the overall structure of the atom. Different amount of charge on the nucleus, different number of electrons already talking to each other. And what I'm going to do is, let me go back to mercury for, mercury's last. Go back to neon before I leave it behind. Here's neon. I'll turn the neon lamp on. I'm going to look at it with a camera, and I'll put it up there. It's the same camera as before. Okay. I'm going to have to come up a bit to get this right. Up you go, come on. Ooh. There we go. So there's a straight shot of the neon lamp. Nothing interesting yet. But I'm now going to look at that neon lamp through what's called a diffraction grading. And diffraction grading is like a grilled mesh of little vertical lines. But instead of being vertical and separated by a centimeter or two like my fingers are, they're separated by really tiny distance on the order of the wavelength of light. And as a result, each light wave coming from that lamp goes through the grill work and actually hits many grills at once and comes out as a collection of partial waves that, as in interference. It's going to come out as lots of little pieces of the original wave. And those pieces continue on. They actually spread out like ripples on a pond. They come out sort of circular, each one individually. But as a team, they come out and they travel broadly across many directions. But there are some directions in which they experience constructive interference and a lot of other directions where they experience destructive interference. So when we look through this grading, and it's up here, and instantly the surface of a CD or DVD looks a lot like a diffraction grading because it has very closely spaced lines inside it. So now we're going to look through the diffraction grading, and it looks like nothing changed because we're still looking straight at the source. And there is constructive interference straight on, but there's also constructive interference over here. There it is. Okay? And I'm looking seemingly at the wrong place. I'm over here. Whoa, why are we over here? Well, it's because the light went through that grading, and it goes through the grading, it experiences constructive interference straight ahead, but it also experiences constructive interference way over here and way over there. And these deflected versions, it's constructive interference, but it's very wavelength dependent. Different wavelengths experience different constructive interference at different angles. And that's why we're seeing all the colors spread out like that. I can actually zoom in. Oops, try to zoom more. Okay. What you're seeing is all the different colors that are actually present in neon. It's not a single red line. It is a mixture of them. And actually it's got some green in it too. You can see all the different colors. There's some green emissions here. There's some yellows and oranges. This should be red, except that by the time you go through all this processing with cameras, which don't see color quite the way we see it, and projectors, which don't present color quite the way we see it, they're all trying to figure out somehow to show you color. And the result is you get these color problems that show up. It's not quite what it should look like. Too much manipulation of the colors. But the point is these lines. These lines correspond to specific radiative transitions where an electron went from a specific orbital to start to a specific orbital to finish. And that the spacing between those orbitals, not in physical space, but in energy, is a certain amount. So in going from this orbital to this orbital, the electron gave up a specific amount of energy. And where does that energy go? It goes out as a photon of light. And light's frequency is exactly proportional to the energy of its photon. So if the energy was this much, the light comes out with a very specific frequency and therefore a specific color. If the energy was a little more, it's going to come out, the photon that was created will have a little more, higher frequency. It'll be a little shifted toward the blue end of the spectrum, and so on. So these are the high energy. This green here, these are higher energy photons produced by some orbital step that was a bigger step, more energy involved. Down here at the end of the red, and they're probably ones we can't see, the camera doesn't detect either, out here in the infrared, that have less energy between the two orbitals. Therefore, the photon that came out carries less energy, is a lower frequency, longer wavelength, and therefore it's somewhere out here in the red or beyond the red, the infrared. Is that okay with people? Or questions about it? So you're seeing the atomic structure, and this is this sort of thing in the, I suppose, the beginning of the 20th century, that is the 1900s, early, trying to figure out how this thing worked was the task at hand. Big deal for everybody there. I'm going to turn off the mercury lamp. Make sure I don't burn my fingers. It's not entirely energy efficient, so it can get warm, but it's not bad. Here's helium. Helium is a much simpler atom, and it should have a much simpler spectrum. Oh yeah, simple city. Okay, it's only got a couple of different lines, very widely separated, because its orbital structure is just so much less complicated. The fewer electrons mean that they're less. There's less sort of negotiating between the electrons. Like, I'll go here from here to there if you move from this one to that one. And that's going on in neon. It's not going on so much in helium. There are two electrons that have to talk to each other, but that's relatively easy. 3 is a crowd. Okay? When these colors come together, all these different, the yellow is clearly the brightest on this screen, and there's a blue that's pretty strong, and together they're giving us the glow that we see with our own eyes. Okay? So these are the color discharge lamps. I should say, the neon red, I've rarely seen, maybe never, an advertising sign that used a gas discharge where you saw the discharge and it wasn't neon. If you can see the discharge, if you see an advertising sign with multiple colored tubes, and one of them is that neon red that you saw, go look at the sign closely. My guess is that the neon tube will be, you'll see a transparent glass with glowing plasma inside. And all the other tubes with their different colors, you won't see the plasma anymore. You will see a powder on the inside surface of the tube, and that powder will be glowing with the color. You okay with the distinction? So where's that powder's glow coming from? And that's where I'm heading. I'm going to put in mercury. Why pick mercury? It seems like a terrible choice. It's a toxic chemical. You don't really want to be incorporating mercury in your body. Back in the day when people made felt hats, they would form the felt hats with hot mercury. They would manipulate it with hot mercury, get mercury all over their hands, breathe the fumes from the hot mercury, and that's how you had Mad as a Hatter. So the Mad Hatter in Alice in Wonderland, what's the origin of that? Working with mercury. It's toxic. Okay, important facts. This is a mercury discharge. Well, that sucks. Is it really going? Yeah, it's got that blue line and one green line and pretty much nothing else. What's going on? It is glowing brightly in the ultraviolet. So the mercury lamp, because of the quirk of mercury's atomic structure, its brightest glow is actually nanometers is 2480, a glow I know too well from my graduate days. I saw that ultraviolet way too much with my own eyes, and anyway, long story. There's almost no visible light coming out of the mercury discharge. And if you remember, I asked you a question early on about if you take a fluorescent lamp and you got rid of the white powder on the inside, would it look brighter, dimmer, brilliantly bright in the middle? Remember that question? Let me show you a fluorescent lamp with, fluorescent lamp with no powder. You happen to have one. It's right here. There's a normal fluorescent lamp. There's the no powder version. Ha-ha. It's very dim. Why is it very dim? It's the same blue. Most of the light is invisible to our eyes. It's ultraviolet light. We can't see it. So far, so good? That seems like, okay, well, why do that? That seems very pointless to have light we can't see. So let me show you the value of having light we can't see. I'm going to stop staring at that. Okay? I can turn this guy off. The ultraviolet light actually never leaves the fluorescent tube. It should be absorbed by the glass, so that although, even in this one, I believe that the shell of that tube is made of ordinary glass. Ordinary glass is not transparent that deep in the ultraviolet. To get the ultraviolet out, you have to use more specialized glass, quartz glass, fused quartz it's called. You don't actually want that light out because it is deep in the ultraviolet. It is therefore does a lot of chemical damage. It's hazardous. Yeah, what about 4 years ago I had cataract surgery. That is, I had my lenses of my eyes replaced because as a graduate student I was exposed to too much ultraviolet from a mercury discharge that did have a transparent tube. You know, stupid things to do as a kid. Okay, that ultraviolet light is supposed to stay inside the tube, but it doesn't do nothing. It's not useless. It's actually quite useful. It exposes a powder on the inside surface of the tube, and that powder isn't just like crushed glass white. It's fluorescent material. That is, it's material that takes in photons at one frequency and emits photons at a different frequency. To conserve energy, standard fluorescence can't emit photons with more energy than the photons that came in, but it can emit them with less. The missing energy typically ends up as thermal energy, but you get the photon in occurs at high frequency and the photon out occurs at lower frequency, like this. This is an ultraviolet flashlight. There, I'm blasting with ultraviolet. This is near ultraviolet. It's almost visible, and it's not very dangerous. So you've seen these your whole life, these neon colors. You know, neon. What's neon about it? It's not, a little bit related to that. It's fluorescent, meaning that I'm sending in photons of ultraviolet light with their large energies. The material in there is absorbing those photons, and it is wasting some of the energy and then re-emitting it as visible light. Okay? Different colors. So there is no visible light here. I mean, it's got a blue because it's near ultraviolet. But the reason you see it is because stuff glows in it, fluoresces in it. My shirt probably does, yeah. My shirt here is glowing. This is not, it's brighter than my hand, right? Not because of, I don't know, my hand's not, the skin's darker than but because this clothing has a blue fluorescent material in it. Most clothing does, certainly most whites these days. They have what are called brighteners. They are fluorescent materials that take in ultraviolet photons and re-emit them as blue. And why that? A paper, same thing. This paper has brightener in it. You're not seeing the ultraviolet, you're seeing blue light emitted by fluorescence from this sheet of paper. And the reason for that is because fabric and everything else tends to go yellow with age. It develops a yellow tinge. Look at old fabrics in the attic. They develop a yellow tinge. The old-fashioned way of solving, because they begin to absorb blue. That's where yellow comes from, remember? Yellow means the absence of blue, so you're losing the blue. How do you replace the blue? The old scheme was to put a dye in that ate the other colors. So you lose blue because of age. You lose reds and greens because of chemicals. And that was called bluing. Back in the day, people were bluing in their wash, which simply just took what used to be white and turns it into gray. So it doesn't look yellow, it looks gray. Okay, bad idea. The modern solution is to put in a chemical that recreates the blue. How does it do that? The missing blue. It does that by fluorescing. Whenever exposed to sunlight or anything that's got ultraviolet in it, it creates the blue. So my shirt's got lots of bluing in it, not bluing in it. It's got fluorescent brightener in it, that fluorescent material. So these are all fluorescent stuff. The Tide orange, these crayons, these are all fluorescent crayons. There's no orange or green light in this flashlight. They're fluorescing. And just to finish this thing, the tubes up there contain a powder, a careful mix of chemicals that fluoresce when exposed to mercury's ultraviolet light. And they fluoresce in a way that creates white light. And they can be tweaked to create white light like a sun or white light like an incandescent light bulb or anything in between. So that's the origins of fluorescent lamp white. They can also be brightly colored, which is how the advertising signs work. So go look at the advertising signs, those tubes. If they're not neon orange, red, they're probably fluorescent tubes with a phosphor that's glowing like these things are. Okay.